All right, so now I want to describe an alternative way of putting a topology, a base of topology on this G hat. Okay, so here let's do the following proposition. So first of all, if I have a K inside a G, okay, and say C inside G hat, they're both compact, and some epsilon is greater than 0. So let's define the following sense. Okay, so let's define the n of K epsilon to be all the phi inside the G hat, where whenever you evaluate this phi x, okay, it's going to be less than 1, minus 1 is going to be less than epsilon, so it's close enough to epsilon for all x inside G. Okay, essentially just saying all the phi where on this compact set, this phi x is close enough to 1. Okay. And similarly, you define the n of C epsilon to be all the x inside G where the phi x minus 1 less than epsilon, but now it's against for all your phi inside this compact subset of the dual group, okay? So the first one is clearly a subset of G hat, and the second one is clearly inside G. I want to show that they're both open, okay? So they are both open. And moreover, I want to show that because they are now open, I want to show that all the, I care more about the subset of G hat. I want to show that these sets, okay, all the n of K epsilon, it's a neighborhood base, okay, so it's a neighborhood base, or basically a base of topology for these G hat at the identity character, okay, basically the unit at the G hat, okay? All right, so basically that describes another way of describing this topology, okay? I have a much easier set, a collection of bases for your topology, okay? So now let's prove this proposition, all right? So proof. So first of all, because I mostly care about the topology on the G hat, so I'm just going to prove the n of K epsilon is open. The proof for NC epsilon is open is kind of very similar. You just swap G and G hat, okay? So let's start. So let's fix n phi 0 inside some n of K epsilon. Essentially, I just want to show that there is some open neighborhood around this phi 0 that's still inside n of K epsilon, okay? Because we have that this phi 0, this joint, this evaluation map where map x phi to phi of x is continuous, okay? So that's for every x inside this K, okay? Because this map x phi to phi x is continuous, and I know that phi 0 of x is close enough to 1, it's within epsilon to 1. Okay, so because of this continuous, I can find some neighborhood of this x, and I can find some neighborhood of the phi 0, so that on these joint neighborhood, the phi x is less than 1 is going to be less than epsilon. Okay, so I should say there exists a neighborhood, let's say x inside Vx, and there's another neighborhood phi 0 inside, let's say Wx, okay? So Vx, Wx are both open in their respective topology, and so that the following thing happens. So for every phi inside the Wx and for every y inside the Vx, I have phi of y minus 1 is also less than epsilon, okay? So phi, because phi 0 x is less than epsilon, minus 1 is less than epsilon, I can make sure the phi y is close enough to phi x, so it's still less than epsilon, okay? So now, well, K is compact, so you do the kind of the standard trick. So K being compact and is contained in all the Vx, x inside K. So there exists a finite subcover. So let's just let it to be x1 up to xn. So let's let K is contained in the union of Vxi, where I go from 1 to n. Okay, so it fixes finitely many of them. All right, so this essentially just shows that for every phi inside, well, let's let W to be the intersection of the corresponding WXI. Okay, so I go from 1 to n. So this essentially just shows that for every phi inside the W, if you consider for every y inside the K, well, this y has to come from one of the VXI, and you have this phi of y minus 1. Well, this phi being in W is inside all of the W of xi. Y is inside one of the Vxi, so you do the calculation, so this is going to be less than epsilon, okay? So in other words, I have that this W, now we know this is open, and everything inside this W will satisfy this condition of n of k epsilon, okay? So W itself is contained in n of k epsilon, okay? So this finished the proof that n of k epsilon is open, okay? So in conclusion, n of k epsilon is going to be open. All right, so not only is open, now I want to show that they actually form a neighborhood basis at the identity, okay? So let's do the second part. So let's essentially, I just need to show that for every open neighborhood of the identity, I can basically find some subset coming from these nk epsilon, okay? Some of these nk epsilon. So let's say for every phi identity, that's the identity character inside open neighborhood, let's call it V. Okay, so because I have these weak star topology, okay, we have these bases for the weak star topology. There exists some function, collection function, let's say f1 up to fn inside L1 of G, and there exists some epsilon 0 greater than 0, so that we have the following. So we have this phi of E is inside U, which is essentially what we defined as, sorry, not phi of E, okay? So let's just write U first, okay? So this U of F1 up to Fn centered at phi of E with this control epsilon 0. So let me remind you by definition, this is all the phi inside G hat, where you integrate the Fi against phi minus phi E. Their integral is going to be less than epsilon, okay? So that's for all I. Okay, we know these are open neighborhood bases for your topology, so this is going to be contained inside the V, okay? So this is contained in V because V is open, okay? So let's now, without loss of generality, because your compactly supported functions are dense in L1 of G, and you can just approximate each of these Fi by some compactly supported. So let's just say, without loss of generality, each of these Fi are compactly supported, okay? And let's just let there, because each of them has some compact support, we only have finitely many of them, their union is still compact. So let's let K to be compact, so that the support of this Fi is inside this K, okay? That's for all I, all right? So what do we have? Okay, so let's consider the following. So let me do a very technical definition first. So let's let epsilon to be the epsilon, well, here I have epsilon 0 before. Now I define a new epsilon to be the epsilon 0 minus, well, over the maximum of the one norm of these Fi, okay? You kind of the maximum of these one norm, you're integrating against these Fi, so you kind of guessed where they come from. But anyway, so if I consider for every phi inside the n of k epsilon, okay, I want to show that this phi is going to be inside this U, okay? So what do I have? Okay, so I have the all right. So I have that if I take the integral of the Fi against phi minus phi e, okay, d mu. All right, so phi e, well, let's just write it out first. This is the integral of the Fix. Phi x minus phi e itself is equal to 1 d mu, okay? And this is going to be less than or equals to the integral of the Fi of x, okay? And then you do the phi x minus 1 d mu, okay? And because your Fi are supported on k, so this is going to be less than or equal to the integral over k. And on the k, the phi x, because it's inside n of k epsilon, that's going to be less than epsilon, okay? So this whole thing is bounded about by epsilon times the integral of the Fi of x over k, but you can now replace k by the whole set, so the integral of Fi, the absolute value, which give you the 1 norm of f, okay? So this is epsilon times the 1 norm of Fi, and this whole thing is going to be less than epsilon 0, okay? So in other words, all of these phi inside nk epsilon is going to be also inside this space U, okay? So in other words, I have phi is inside U, so this n of k epsilon is contained inside U, which is contained in V, okay? So because U is open and you now have a neighborhood base nk epsilon, okay? So as an immediate corollary, once you have the topology, so these description, you can talk about a new topology on the G hat. Okay, so the topology on the G hat is actually generated by the elements of the form where you have nku, where let's define it as all the phi, so that the phi x is inside U for all x inside some compact set k. So here, k is compact, U is open. Okay, so U is an open set in the unit circle. K is going to be compact on G. Okay, so the topology on this G hat is on one hand is the weak star topology, but on the other hand is also this also called the compact open topology. Okay, so this is also called the compact open topology. So in some reference, you can, well, they will say the G hat has the compact open topology. Don't need to be afraid, it's essentially the same as the weak star topology, all right?